Thank you, Lisa. Thank you very much, Lisa, for the introduction, and thank you for being here, and thank you also for following online at home. It's really a pleasure and a great honor to stand here in front of you at this sacred ground. I've been inside Faraday's cage, but I've never been in Faraday's theater, so I feel really these giants here looking over my shoulders with me. So again, it's really a pleasure to be here. Thanks to the Raleigh Institution for inviting me, and also special thanks to the Netherlands Embassy for organizing this and having these Dutch science lectures. Today, I'll talk with you for about an hour about materializing intelligence. And that sounds maybe a little bit weird. Intelligent matter, information processing, what do we mean with that? I'll hope that become a lot clearer in the coming 60 minutes. And otherwise, there will be Q&A, in which I'm very happy to discuss with you here and online. Let me proceed with the most important view graph of tonight, and that's the acknowledgement slide where you see all my co-workers present and also former ones. I won't name them all, but I will point out their names when I discuss some of their work. I think what's important to mention is that when you talk about intelligent matter, material learning, all these things that I'll discuss tonight, many traditional disciplines come together. So my background is in applied physics, but we'll see that there's contribution from computer science, from mathematics, from chemistry, and a lot of more wild combinations actually that we see in our research, and that makes it also very exciting. So I would like to talk about learning with you, and I hope we all learn tonight. And I think you're all familiar with the concept of learning, because that's what we basically have been doing from the moment that we set foot on this planet, and it continues basically till you die. And so what's important to realize is that learning means really a physical change in your brain. There is really something changing. Hopefully, but when you leave this theater tonight, there has been some new connections. Maybe some connections have been broken, some reinforced, but there's really a physical change in your brain, in your board computer, maybe, if you like to call it like that. And that's already a very important aspect that I would like to stress, is that information processing in biological systems, and the human brain in particular, is really something material, something physical. And I would like to contrast that with maybe some of our man-made technology. As I said, learning is taking place at any age, and this is this famous Faraday's lecture, Christmas lecture in 1856. Standing right here at this desk where I'm talking tonight. So, what's actually so special about this brain of ours? Well, maybe just to give you a context, we're talking about nearly 100 billion neurons, and there's sometimes some confusion about billions, so I put it down in the scientific notation, 86 times 10 to the 9th, so that means 9 zeros coming. So this is really an astronomical number of neurons, but it gets even wilder because each neuron can connect up to 10,000 other neurons. So we are really talking about a super dense network. And then these other neurons, these connections are formed by synapses. So I'll show that in a moment a bit more in detail. But these connections are plastic. They can change. They can get stronger or they can get weaker. And there again is this plasticity that's so important in the process of learning and memorizing for the long term, but also the short term. And all these connections, all these neurons, allow for an amazing amount of operations per second. And of course, it's a little bit hard to make a direct comparison to our digital computers, but we are still, if you look at 1,000 trillion operations per second, so there's a 1 with 15 zeros, and we are still orders of magnitude away of what we can do with our processors. And it only weighs 1.5 kilograms or so, so we can walk around with it. But for me, the most amazing aspect is its power consumption. It's just about 20 watt. So maybe you remember these old light bulbs. They were typically 60, maybe 100 watts. Our brain consumes much less than that. So how is it possible that this natural machine can operate at this very low power consumption and do all these amazing things and do many things also in parallel? We'll get to that. So zooming in a little bit more on the physiology of the brain, after I zoom in on the nerve cells or the neurons. So maybe it's fair to say that there's a lot of things, maybe most of the things we don't yet understand about the brain and how things like cognition and consciousness work, but there are of course a couple of things that we do understand and that we know in quite high degree of detail. And that's, for example, how the neurons architecture look like. So we have a cell body, or the soma, where signals from other neurons are collected, and then at the end there is an axon. So basically there is again a lead leading to yet another series of neurons via these terminal buttons, where you have these connections, these synapses, these learnable weighted connections that finally connect to other neurons. So these enable for this very high and densely branched network. So dendrites coming in, collecting the signals, and then in the soma all these signals are being collected, and when some threshold is being passed, then there is a signal firing, and we call this an action potential. So depending on the signals that arrive at this neuron cell body, there will be a moment that the sum of these input signals crosses a certain threshold value, and from then a spike is being sent along the axon, and that is then being fed through to the other neurons that are being connected to it. So that's also a very interesting and important aspect that we'll see later on also when we start to look at models and also hardware based on the brain. Zooming a little bit more on this synapse, as I already said, basically there is where the learning can take place. It's not only an electrical signal there, but there's also a transfer to chemical signals. So we call those neurotransmitters. And depending on the signals that get through this synapse can get stronger or weaker. And one of the kind of central paradigms and theories of learning was proposed by Hebb and is now referred to as Hebbian learning. And the kind of popular way of summarizing it is saying cells that fire together wire together. What means that if you have many signals passing through a certain synapse, there is a tendency that these connections will get stronger. So that is a kind of plastic change, whereas if there is for a longer time no activation across a synapse, these connections will get weaker. And in this way, there will be a kind of possibility to plastically change the network depending on the signals that it processes. So what you see here is that processing, but also storage and memory, basically are co-located. It takes place at the same physical place in the machine that we call the brain. Okay, so this is all about signal processing, maybe information processing, and also what we understand nowadays about how learning works at a very basic level. If we get to a much tougher problem to define, it's intelligence. Intelligence, there is not really a unique and all agreed upon definition of intelligence. And what you do in such a case, then you of course go to Wikipedia, and there you can find that intelligence is defined as ability to perceive or infer information and to retain it as knowledge to be applied towards adaptive behaviors within an environment or context. So this is a very long, complicated definition, but it's maybe good to pick out a couple of elements. So first of all, try to get in information, to receive, to have an input of information. Retain it. There is some aspect of memory there. You want to store that information. And then you would like to base your behavior on it. So you would like to act on it. And you would like to do that in a way that adapts, that is adapting to the environment around it, so that you can basically, based on inputs that you receive, you can determine what your actual acts are gonna be. That can be determined by the here and now, but it can also be based on the past, because you have this ability to retain this knowledge. So that's a kind of very generic way of defining intelligence, and it gives us some handle if we would like to go to intelligent matter. So what are the kind of necessary ingredients that you would have to kind of design into your material, or what material maybe can offer you naturally to become something like intelligent? And I again have to make a big disclaimer here that this excuse me, this intelligence has nothing to do with things like consciousness or emotion or things like this. As we are trying to get a kind of engineering basic grip on what intelligence is and what it should be if we materialize that, if we try to get that incorporated in inanimate matter. And of course, all these things like emotion, psychology, consciousness, these are things that are even for brain scientists very hard still to understand and to describe. Okay, so this is a kind of very dry definition of intelligence, if you like. Maybe just to contrast it with one of the greatest thinkers of our time. Of course, intelligence is not just about memorizing all kinds of facts, but try to come up with new concepts, with new ideas to shape, to create, to imagine new things. And I can't agree more with that. And I think that's one of the most amazing things of what the brain can do, is really come up with completely new things and come up with kind of chaotic patterns that lead to new ideas, music, literature, whatever, science. So far, it was all about biology. It was about organic, wet tissue. It was about us. But of course, all these ideas and observations about intelligence have inspired people to look and to look at something like artificial intelligence. So can we create machines? Can we create algorithms? Can we create robots or so that can somehow approach or maybe even emulate this biological intelligence? And very broadly speaking, you could define that field as artificial intelligence. And I think it's good that you have a little bit an idea of where this field started and where we are now. So artificial intelligence conceptually was put forward somewhere in the 50s of last century, when people started to think about concepts, how you can, maybe in an abstract way, kind of mimic the brain. And in general, you can call artificial intelligence a kind of school of engineering, where you try to make intelligent machines or other kind of programs, software models, or whatsoever. But man-made systems, which have some properties that you could define as intelligence, in the sense that I discussed and defined before. Then if you zoom in, artificial intelligence is quite broad, it's quite generic. Then if you look a little bit further, then in time, so you come then in the 80s or 90s or so, you start seeing a kind of nascence of what is called machine learning. And machine learning is basically a way of making models. Basically, we still talk about software, we talk about mathematical models, where you don't program line by line, as a good computer programmer would do, what you would do in a certain situation, that you have this kind of if-then loops. If this is happen, if the animal is green, then maybe it's a frog, and if not, then go to line 60, and so on. So where you basically have kind of very well-defined program lines which you go through in order to come to a solution. Instead of that, machine learning has a very different concept based on artificial neural networks that need to be trained, where the general structure is given, but basically where the starting model is still completely agnostic, can't do anything till the moment that you have trained it, that you have gone through a cycle or multiple cycles of learning, the so-called machine learning, and only then your model, your algorithm is able to solve certain problems. I'll get back to that in a moment. And perhaps some of you have heard this now famous term, deep learning. There's a lot of talk about deep learning. You hear about maybe Google Translate, deep learning, and image recognition, and this kind of things. Basically, deep learning is a branch of machine learning where you go to very, very extended models, mathematical models, so-called deep models, which contain many layers that can really tackle very complicated problems like processing video information and recognizing all kinds of speech, visual information, and so on. Of course, all these models are more or less loose or less loosely based on the human brain. That has been the big source of inspiration for this uprise of AI and machine learning and deep learning in particular. So let's look again a little bit on back at the biology, but now really in this very abstract fashion. So maybe you remember that we had this cell body. So this is the cell body of the neuron, which collects signals via the dendrites, and then at the interface there are the synapses, which are kind of weights, the learnable weights here. And then finally, if there is a threshold being reached, then an action potential, an electrical spike, is being sent along the axon along to a next series of neurons. And this is a kind of the essence, if you like, of the biological neuron. And then the neural network will be then a very vast interconnection of these building blocks that we have here. So if you look now at the kind of basic structure of an artificial neural network, it uses basically this as a building block, this artificial neuron that is based on this biological, very abstract form, and then interconnected in different layers. So the building block for artificial neural networks was already introduced in 1956 by Rosenblatt. It's called the perceptron, and as you'll see, it looked very much like this biological neuron that I introduced. You'll see that you have input signals here. These blue dots, they are the input signals. They are now really abstract. So the perceptron is a mathematical model. There's nothing physical about it. And then, very importantly, these inputs are being multiplied by weights, by numbers. Finally, they go into this red summation block. So this would correspond with the soma, with the cell body, in which these incoming signals, the weighted incoming signals, are being summed and also compared with a threshold. Once this threshold is reached, then there will be a step in a mathematical function. This is the threshold function, and then a value will suddenly change from 0 to 1 or from -1 to 1. And so you can see the analogy with the biological system there. When a certain threshold value is being reached, an action potential is being sent out. And here, excuse me, it's simply that a function changes its value very abruptly in a steep fashion. And this is a kind of the decision maker of the artificial neuron. So there's basically a kind of one-to-one correspondence between the biological neuron and this perceptron or single artificial neuron. And like in our case, that a single neuron cannot really solve problems, you also have to interconnect these artificial neurons to get to some solving functionality. So here you see an example of what you could call a deep neural network. You see that you have all these building blocks here, these artificial neurons or perceptrons, and they are fully interconnected. So all these lines correspond with interconnections, and they're also being weighted. So every line has a certain weight with it. Now, the big task of machine learning and deep learning in particular is finding the values of these weights and finding the values of the thresholds in order to solve a certain problem. And in this case, I have a kind of toy problem for you, recognizing or telling apart pictures from 4 different animals. So we have cats, we have dogs, ducks and frogs here. And you could write a whole computer program and looking at all the details and see to figure out what these animals are, if you feed it all kind of pictures. But that's not the way machine learning works. No, it basically feeds these images, many of these images, to the model, to the deep neural network. For example, in the form of pixels or other digitized ways. It can be analog as well. And then you would do basically a learning step. So for example, if you present a picture of a dog, you would like that basically the lamp or here starts burning of dog. And if you present a picture of a cat, you want that here some signal goes off and not here, and not here, and not there. And the way you have to do that is also a mathematical puzzle, basically. There are algorithms by now that help you to find these weights and thresholds in a guided procedure. There are, for the specialists, things like backpropagation and gradient descent, that for these certain class of neural networks, there are actually many more, but this is a certain class called feed-forward neural networks. They can solve this and find a kind of optimum based on the data that you feed it to solve this puzzle. So finally, if you have fed it maybe thousands or 10,000s or 100,000s of images, at the end of the day, your model is able to give the answer, okay, this is a cat, or this is a duck, or this is a frog. Even if you come with pictures that the model has never seen before, right? However, if you come with a picture of a truck, or if you come with a picture of a melon, yeah, this model cannot say anything about it. Probably it will get anywhere close, maybe says, okay, it's a frog or a cat, because it only thinks in that kind of language. And so it's a very specialized machine only being trained for a certain task. So it's a very special purpose machine, or some people call this a one-trick pony kind of thing. But nevertheless, this is very powerful, and many of the applications that you probably use on a daily basis are being based on this kind of deep learning, which takes place hidden from your eyes in, for example, data centers. Because you can imagine that finding all these weights, all these thresholds, all these interconnects, and updating them all the time, and going through these iteration loops to find a solution based on these 10 or 100,000 of data points that you feed it, is very time consuming, but also very energy consuming, very power hungry. And this is illustrated by the graph that you can see here. This is a kind of history of training artificial intelligence system or neural network systems, where along the vertical axis there is basically a kind of measure of computing power, compute number of steps that you, number of calculations that you have to do, ergo also a certain price tag that comes to it with energy. And nowadays, as you know, this energy tag will only rise more and more. Interesting to see here is that in the beginning of these machine learning, speech recognition, this is image recognition, basically till 2010 or so, there has been a trend that is having the same pace as this famous Moore's law that you may have heard about. Moore's law is basically a hardware prediction which says that roughly every 2 years the number of transistors on a chip double. A prediction made in 1965 by Gordon Moore, one of the co-founders of Intel. And it has actually turned into a kind of self-fulfilling prophecy, because the semiconductor industry kind of took a ruler and said, okay, where does Gordon Moore, where we need to be in 2 years, and then they adjusted the theory. And miraculously, this has been going on for a long time, and still with some tricks here and there, you could argue that Moore's law is still more or less holding in. It becomes more less than more, actually. But very dramatically here you see this kind of kink in the tendency coming here in the year 2012 or so, where you see a much higher increase of compute than basically hardware can keep trace with. And that has to do basically with the kick-in of this deep learning and this massive explosion of AI. So basically the need of computing resources doubles now every 3 or 4 months, so at a much higher pace than hardware can keep up with. And this explosion of AI, or some people call it a kind of the renaissance of AI, can be explained by 2 factors. On the one hand, it's the availability of computing power. Our traditional computers become more powerful, so you can do those things, and also the availability of big data. So the internet, of course, there's a huge amount of data available on which you can train these neural network models. So those 2 important factors why you see this exponential takeoff of AI and machine learning. But this is, of course, also a problem, because you can imagine that this is non-sustainable. An example here, also from a British company, DeepMind, obtained by Google, is here this machine learning system, this AI system playing against this Korean Go player. I just had a Korean cup of coffee just before this lecture, so maybe I also have a chance in playing Go. I don't think there's a lot of chance. But this guy, this poor guy, I should say, with only a brain of 20 watts, won only 1 out of 5 matches in this tournament, and was beaten by this kind of artificial system playing the game of Go. And I've been told Go is many, many, many more times complicated than chess, for example. The solution space, the number of positions on the board is astronomically larger than games like chess or checkers. And so people have thought it's impossible, it takes another decade before a machine can beat man in this game. But it happened, and it became stronger and stronger. This is 2016, but by now it has become already much stronger. But, as I said, under the carpet or behind the screen, there is, beating this 20 watts here, there is a huge amount of compute going on. There is nearly 2,000 of processors and nearly 300 of graphic processing units consuming about 1 megawatt that is being burned in order to keep up with this single person. So you can imagine this is a kind of unfair game there. And if you would like to scale that, it's virtually impossible. And that's also illustrated by this graph here on the left, where you see that the electricity consumption of ICT, so things like internet, computing, and data center, and all together, is really taking off exponentially. And by 2030, in this prediction, will already be 20% of the total electricity production. So not in addition to maybe lighting and other consuming electric trains, whatever. So really a sizable amount of energy is consumed by ICT. If you look here on the right, this is an article of one of the TV stations, which says that new data centers that are planned for the Netherlands will consume about an amount of energy which is twice as high as of the whole city of Amsterdam. And so these are astronomical numbers, which already give you a hint that this is really not the way to go, especially if you want to do the computing in a non-local fashion. So, for example, like in this self-driving car. So, how is it possible that that our technology can't meet the requirements and can't really do this in an efficient way? And this really has to do with the architecture of our digital computers. So our current digital computing hardware has a separated processor and memory. That means that all the time memory and data have to be shuffled between this memory and the processor, which is often over a larger distance consuming a lot of energy. It's very power-hungry architecture. Our man-made systems are very good at doing exact calculations, but very poor at doing cognitive tasks and image recognition, for example. And also we have to realize that our hardware is based on the brilliant ideas of Alan Turing, but is a very sequential, it's an intrinsically sequential machine where you calculate step by step. Very different from networks like the brain, where many things are happening in parallel. As I try to make clear in the explanation of these neurons, is that their memory and processing is co-located at the synapses, for example. It takes place at physically the same place. You have these 10 to the 15 operations only for 20 watts, roughly speaking. And that, where the brain is maybe not so good at these exact calculations, it's very evolved towards doing this kind of fuzzy things like image recognition, cognitive tasks, trying to gauge the environment. And this all happens massively parallel. This is one of the main ingredients. So we basically should go to implement a kind of brain-inspired computer chip. That's the message. So we should go to hardware, not only software models. So far I've been talking about software based on the brain. Now we should also go to hardware. And this is a field that is referred to as neuromorphic engineering. So neuron from neuron and morphic, shape, so kind of neuron-shaped engineering. Okay, it's time for a small intermezzo. I've been told as a teacher you should not only be sending, but you should also be receiving. So I would like to confront you with this mathematical puzzle. I know it's a little bit late, in the Netherlands even a bit later, but maybe you can solve this puzzle for me. Is there a volunteer? Yes. 2000. Yeah, 2816. Okay. And we have a winner. We actually have two winners. Indeed, 2816. Okay, I would like you now to concentrate very much on the screen. Bear with me. For a split second, you saw an image. What did you see? Mr. Bean. A baby. A scary baby. Okay, a scary Mr. Bean baby. This sounds to me rather ridiculous, but okay. You are the British here, so you should be able to recognize Mr. Bean. Indeed. I hope you never saw this picture before, but you were able to recognize this picture in a split second. And with all honor, you had quite some difficulty with solving this mathematical puzzle, right? So just to illustrate that our brain is not very good at doing this exact calculation. Maybe we didn't need that in our evolution, right? To count how many leaves there were on the tree. As long as we saw there was a lion under the tree, it was enough, right? We had to recognize in a split second. So our brain is very, very good at that. Okay, end of the intermezzo. We continue with the story, and that basically says, forget about only concentrating on this software, but also look at hardware. And that is what industry actually has been doing. So all the big names, nearly all the big names you can see here, we have IBM, we have Intel, Google, Apple, and what they have done is over the years, till very recently, till actually this month, introducing a kind of specific, special purpose, application-specific integrated circuits, or IC, for these AI tasks. Specifically also for calculating through these neural networks. All the calculations that have to be done. There's many multiplications and additions that are involved in calculating these neural networks. They designed chips that can do that much more efficiently. Why? Because they have found ways, architectures, to partly circumvent maybe this von Neumann bottleneck. This von Neumann bottleneck is the bottleneck that you have memory and processing separated, and that you all the time are shuffling this data between memory and processor. They refer to that as the von Neumann bottleneck, because von Neumann was the person who basically suggested the first architecture for a digital electronic computer, which basically is still being used today. They try to parallelize operations by making multi-core architectures, for example. But basically it's still digital. It's digital technology using zeros and ones, where you only basically use material as a switch, on and off, black or white. So only a very limited spectrum of materials that you use. Also using conventional building blocks, transistors. Conventional materials, semiconductors, silicon in particular, are still being used. And still, even there are amazing progress to be reported, still we are orders away from the efficiency of the human brain. So yes, things are being done there, but we are not there yet. And it's very hard to conceive that based on traditional building blocks, traditional materials, will get to a solution of this energy consumption explosion that I just showed you before. So I come back to learning. I've been talking with you about biological learning. I've introduced very briefly to you machine learning. I would like to talk with you about material learning now. What is material learning? basically asking ourselves the question how to exploit the intrinsic physical properties of materials to compute, to process information. So is there more hidden in materials than just on and off, low or high, black or white than that? And a very interesting question to ask is there really something unique about the meat of our brains? Or is there just a whole other range of materials that could more or less do the same as our brain can do, or maybe even better, maybe even more efficient, or in a smaller volume? And of course, and that's basically here, can we then compute efficiently using a material that we could dub intelligent? And I come to what we may call intelligent matter in a moment. But to illustrate that this idea is not new, that you have to do a lot of calculations, a lot of operations to calculate relatively simple things of nature. So, for example, like a drop of ink diffusing in a glass of water here, we can see it in front of our eyes, what happens and how it diffuses through. But if you have to calculate it, you have to solve a lot of differential equations, do a lot of machinery, whereas the glass of water, so to say, is basically calculating the pattern for you for free and on the spot. And that's a kind of the philosophy here put forward by Richard Feynman when he says that it's quite amazing that you need so many calculations, even if you have to calculate the evolution of a tiny piece of matter over a very short time. Okay, so I already said intelligence is a very tricky thing to define in general sense, but here we do an attempt to define what intelligent matter is for inanimate matter. And we have laid that out in a recent paper, my colleagues in Münster and myself. And basically what we have defined and proposed as necessary elements is that for a matter to have a chance to be intelligent, it should have a kind of sensor ability. So the ability to receive information. It should be able to actuate, to give some reaction. There should be some network property, some built-in feedback, so that multiple signals can be trained or can be treated at the same time. So you can have more complex functionality in such a network. And last but not least, you also need a storage, you need memory. And then I'm talking about long-term memory and really plasticity in order to enable learning. Nonlinearity also I added because it's a very important decision kind of making concept that you need in this system. So if you now look at different degrees of matter, you could start with the simplest form here on the left that we could call structural matter. And so you could think of a wooden club where the functionality is only derived from the shape and from the structure of the material, in this case wood or aluminum or whatever. That's kind of the lowest complexity you could imagine. If you go to responsive systems, you will have a material that is able to sense, to get some input, like light in this example, and also to respond to that. But it will always respond in one and the same matter. The next level of complexity would be adaptive matter, where you will have still stimuli, you will have some output, but depending on the combination of stimuli, of inputs that it receives, it will be able to adapt. For example, there will be light, there will be temperature, there will be maybe pressure, and enabled by this network functionality and feedback, there will be a response that is adaptive. So it's not always the same, but dependent on the here and the now. And then the last step of complexity that we identify is then the so-called intelligent matter, which also has memory, which has long-term storage, where the response is now adaptive, but not only dependent on stimuli that it receives in the here and now, but also from the past. And so it can also take into account experiences, triggers from the past, and then we have a kind of engineering definition of what you could consider intelligent matter. So to give that a little bit arms and legs, here is a lady with these sunglasses that color if you go out in the sun. So structure is coming from the shape and the material of the lens. So this on the left side is just a transparent glass. So this would be the structure. If you have now the glass that becomes darker if you go out in the sun, then it will be a responsive material. If you have a glass that adjusts its color to the jacket of this lady, so today it's brown, so the glass gets brown, maybe tomorrow it's a blue jacket and will get blue, then maybe it's an adaptive material. And now if this glass is also to remember what she did yesterday, and maybe she went by car in the morning and then it adjusts the focus according to driving, then you could say, well, this is maybe something that becomes like an intelligent matter example. This is just a short illustration of what you could think of in terms of intelligent matter. Of course, we know from the living world around us that there is a lot of intelligence. This is a piece from a Dutch newspaper, but you can see the ideal lies in the arms of the octopus. And what is interesting about these arms of the octopus is that there are a lot of decentralized intelligence. So a large part of the brain of the octopus is actually not central nervous, but distributed over these arms. And so there is instantaneous here response already, coloring and sensing, actuation happening right at the spot there. Okay, so when we were thinking in our lab how to realize this network, sensing, actuation, tunability, nonlinearity, one of the ideas that we came up with was this network of gold nanoparticles. This is a disordered nanoparticle network system of nanoparticles of 20 nanometer in size, which have some organic wrap around them, and which are kind of dropped on electrodes on a chip. So like the chips that we know from our telephones, but much more specialized. And in this case, we have gold electrodes on which we drop these gold nanoparticles. And we thought, can we now learn this material system some trick? Can it do some functionality? And the reason we thought this may work is that the elements, these individual gold nanoparticles, are very nonlinear building blocks. I don't have time to go in all the details, but depending on the voltage you have applied or drops over these nanoparticles, they can kind of spike. Depending on the voltage, you can get a spike in the current. I said this is a nanoscale device, and I guess not many of you are working with nano on a daily basis. So I want to do another intermezzo with you. It is an experiment, but I have agreed with the organizers that participation is absolutely at own risk. There is no liability either for me personally or for the Royal Institution. If you still feel free to take the chicken exit, otherwise please join me in the experiment. It's probably your first nano experiment in your life, which works as follows. If you are right-handed, please take your right thumb. If you are left-handed, take your left thumb. And hold it in good focus. Focus on your nail on your thumb. Everybody there? Yeah, see, also at home. Very good. Okay. You just completed your first nanoscale experiment, because in the snap of my finger, 1 second, your nail has grown by 1 nanometer. If you don't believe me, here's the math. Roughly 3 millimeters per month. Maybe if you eat very well, a bit more. Then 3 millimeter per 31 times 24 times 3600 seconds. This is 1 millionth of a millimeter per second, or 10 to the minus 9 meter per second, which is exactly 1 nanometer per second. So you can calculate that back at home. But this is how enormously small a nanometer is, and we, but also basically your chip makers, are manipulating matter at this scale. Going back to these nanoparticles. So we know how to describe single nanoparticles very well. This is textbook physics. We have to go to ridiculously low temperatures, but I'll skip that. But in principle, the behavior of single nanoparticles is understood. But we have no clue whatsoever how this hopeless bunch of nanoparticles will behave and if we start to apply particles. So even if you can't describe it, then how can we even hope that we can get some functionality out of it? And there evolution comes again to help. Our brain is of course the product of years, millions, maybe billion years of evolution. We don't have that much time in a PhD lifetime, so we have to speed up a little bit the evolution. And we do that aided by a standard computing. We call this procedure evolution in matter. What we do is we take our material system, we apply physical input or physical inputs, so several inputs, and we measure the physical output under a certain configuration. Configuration meaning in our case a set of voltages. Then, based on that input-output relationship, we start to play and change the configuration. And that's where the evolution part comes in. We do that using kind of genetic tricks. We do, for example, selection. We choose the best configurations, but also we do things like crossbreeding. So we have different configurations that we combine to get at a new individual. Or we introduce sudden changes called mutations. And in this way, if we iterate a number of times, typically 40, 50, maybe 60 cycles, we hope that we have come to an input-output relationship that is fit enough for purpose, that is satisfactory, that does the job that we would like to achieve. And that's the procedure. And here in this example, we try to realize as a toy problem, as a proof of principle, so-called Boolean logic. So logic gates that are a kind of the building blocks of logic, also for digital computers, but also important in a wider context. So we apply inputs as voltages to this device. High voltage is a logical 1, low voltage is a logical 0. And what we want for an AND gate, for example, we want that only there is a high output, a logical 1, if both inputs are 1. In other cases, it should be 0. Yeah? And different Boolean logic gates have different truth tables. But let's concentrate on this AND gate. So we would like to have high input here, then we also like to have a high output here at the current. So voltages go here in, and the rest of the contacts are defining the configuration also by applying voltages. So we basically play with the electronic landscape of the device such that the flow of current through this device meets the desired functionality. In this case, a logical AND gate. And what you can see here in the schematic is that what you adjust is basically the kind of artificial genes of your system, illustrated here by these colored bars and represented by these voltages. And in this example, we have reached this functionality as we like. The interesting thing is now that in this device of ours, here you see an atomic force microscope image of the device where you can't see the individual particles, but you see a kind of this plum pudding. It's able to realize all possible Boolean logic gates, so not only the AND, but also the OR, XOR, and so on, in one and the same device, but by changing the configuration. So we can learn, we can do a kind of training cycle to get the functionality in the device. Whereas a priori, basically the device can't do anything, right? It's not exhibiting the desired functionality. Maybe some of you have noticed this T is 300 millik. This is a very low temperature. I also hinted before, this is roughly around minus 272 degrees C. So this is a very academic kind of demonstration. Very nice for us scientists, but not very useful, not very handy to put in your mobile phone or something. So we have moved to another system where we basically also have a disordered nanoscale network. In this case, it's not a network of gold nanoparticles, but it is a network of individual boron atoms. And still, the trick is again the same. We apply voltages in the periphery, we measure current, and with the remaining electrodes, we try to kind of mold the potential landscape such that we get the desired functionality. So again, we do this material learning here using an evolutionary approach. What again is key of this device is that it can sense, it can actuate, we can tune it, and it's also very non-linear. So you see this kind of curve behavior points out this non-linear behavior so that we can use this as a building block. We call these dopant network processing units because they are based on this network of dopants, which are these Bohr atoms that are kind of guests inside a silicon host. To give you maybe a little bit more an image of how this, how we intuitively see this, how we depict this, we have these electrodes here. The two red electrodes where we apply the inputs. Then we start playing with the configuration till we get an output that is desired. And in this example, the puzzle is recognizing a certain handwritten digit, number 7. And we want to train it such that it really gives the right answer. This is a kind of simplified picture, but what is important here that you really start to play around with this potential landscape enabled by the control voltages. And also in this example, we were able, with this device, we were able to get this Boolean logic and also realize that at room temperature, which is of course where we would like to be. Now you can say, well, Boolean logic, we know how to do that. We can also do that with digital electronics, so why are you so much stressing this? Again, this is a proof of principle, this is an illustration, but not only that, because you can also see certain gates as a classification problem. So here, this is the so-called exclusive OR, which is only high if and only if one of the inputs is high. So high is here a red, illustrated by a red dot. So you see here, only one of the inputs is high, then you have a red dot, or here you have a red dot, otherwise not. This is, you could see as a Boolean logic gate, but you can also see it as a classification puzzle. As you can say, can you find a kind of boundary between these two classes of red dots and blue squares? And you will find out that it's impossible to find just a straight line that separates them. You have to go to some kind of circular decision boundary. So we call this a linearly inseparable problem. But if you now transform this problem to a higher dimension, so in this case from 2D to 3D, you can get a situation where you can find an easy dividing plane between the two. And then afterwards the problem becomes relatively easy to classify. So you go first to a higher dimension, you make your problem apparently first more complicated, but after that classification becomes easier. Of course, the problem is how to find this transformation that does that trick for you. And normally that's a lot of calculation. But with our device, we can do the transformation kind of intrinsically by molding this potential landscape in a shape so that in one shot, in one go, it does this calculation for you and makes the makes the classification easier. And so that's the kind of the trick. By using the massive parallelism of your material and also all the interactions that naturally are built in this complicated system of charges and electric fields and currents and so on, you can do calculations in much less steps than you would need if you would go through a sequence of standard digital operations. And hopefully we can extend that philosophy to more and more complex problems. One example is here this famous set of handwritten digits. This is a set of 60,000 handwritten digits that also has been used to benchmark machine learning models. We use that here also to benchmark our material learning system. And we make a step which is called feature extraction. We would like to use our hardware device as a kind of feature extractor. What people have found, in particular these famous researchers Wiel and Wiel, is that particular areas in the neocortex of the brain of the mammalian brain, in this case a cat, are very sensitive to very specific orientations of features. So here you see in the visual area that only for a specific angle of this bar, neurons start firing, either vertical, horizontal, or under a certain angle. So that means parts of the brain are really sensitive for very abstract information. And finally, that is then fed through to more complex structures. So what we have done in a very abstract way is making also feature extractors for certain patterns, in this case 2 by 2 pixel patterns, 16 differences you can get in this way, and every time we have trained a device that can pick out one of these features so that we can finally make the classification of these handwritten digits easier. So again, we go back to this idea of you start with a problem, you first blow it up. In this case, we do that by multiplying with all these feature extractors. So we have like an 11,000 dimensional space or so, something crazy like that. But although this is a huge space, after that classification becomes a lot easier, because basically we have kind of tore apart the data so that we can draw now linear separators, whereas before that was very hard to do. So using this approach, we find an accuracy of about 96% of accuracy, 96% accuracy over this test data set of 10,000 digits, which is not as good as these deep neural networks can do nowadays, but significantly better than if you only do linear classification. Well, what we hope is that finally we can do this not just in the lab, but also in devices at very high speeds, so that we can start to compete with digital electronics and also do that at a very low energy budget. I'll skip a little bit here because we are running out of time, but I would like to discuss briefly with you what is next. After I've illustrated a couple of the basic building block that we are using, this dopant network processing unit that can do some of these benchmark tasks, but there's obviously still a lot of work to be done. So what's next for our nanoscale processors? Well, first of all, we are really looking now at individual building blocks, these single networks of nanoscale elements. So could we start to make networks out of these networks so we get a kind of nested architecture? And an example you see here in this image, where we basically start to interconnect multiple networks. And the interesting thing is, although in hardware it's still a little bit tricky to do, you can do that also with models. And you can show that if you start to interconnect the individual building blocks, you can solve problems that are more complex than that you can solve by an individual unit. Of course, we have to speed up, because one of the things is efficiency. So we try to do that. We have to make our setups faster so that we can run problems in shorter time. Very importantly, we want to incorporate local memory. So now we still store a lot of the memory outside. These networks have to have this plasticity that I've been stressing so much in the introduction, because that's where you can fight this von Neumann bottleneck, co-location of memory and processing. And we are on the way to that, so that the physics of our devices enables also this local memory. And then we would like to integrate with other platforms. So with traditional electronics, digital electronics, and maybe optics and mechanical or whatsoever, so that finally we can make platforms that combine basically the best of different worlds. And one example is a European project called High Brain that we just started this year, in which we combine our platform with that of photonics, photonic processes, and also other analog electronics. So really try to get best for purpose hardware combined in a unified project. So we would like to really go and attack this at the edge computing problem. So for example, where you really want to do delocalized computing, you don't want to communicate with a data center like in smartphones or in self-driving cars. We want to do that very fast and also very efficient. We do that with not only the University of Twente, but also University of Oxford. So here is the Netherlands and the UK, and of course also with some other European partners. And thank God it's still possible to collaborate even after Brexit, although much harder, but luckily we managed between EU and the UK. And I hope that will get easier and easier again, because this is really where interesting cross-fertilization happens. So to finish, what's next for materializing intelligence? It's very hard to predict. I think the most interesting things will happen where we have no idea whatsoever. I've just indicated here some colleagues of mine, some friends of mine on both sides of the North Sea that look at very different ways of materializing intelligence. Like, for example, Martin van Hecke in Amsterdam. He works with mechanical systems, soft materials, rubber. He talks about a rubber computer. So he shows brilliant things how you can let a piece of rubber basically under the influence of some pressure solve problems for you. Susan Stepney works with magnetic architecture. She is one of the basically founding mothers, I should say in her case, of this field of natural computing based on materials. Very nice person with very nice research also in this field. Dear friend of mine, also Alex Kajetorians, works with quantum-based systems and try to use basically the resource of quantum to get this brain-like models. And last but not least, colleague also in the High Brain project, Harish Bhaskaran, works with phase change materials like the ones that you also have in Blu-ray disc, for example, to use them as storage of weights in these neural networks. So you can, by changing by light or by electricity, you can change the weights and in this way have plasticity that you would like to have. So these are just 4 examples of just people in the Netherlands and UK, because this is, of course, an NL UK event. But all over the world, people are looking at a whole range of material systems, organic, inorganic, nano, micro, whatever, even at larger scale, in order to try to get information processing done in materials, and using the richness that materials have to offer, and step away from this just 0-1 paradigm that is very powerful for digital computing, but also very limiting. So with that, I conclude. I've been talking about the transition from machine learning to material learning. I've been stressing to use the intrinsic, physical, especially nonlinear properties of matter for computing. You can even use designless systems like our system, not necessarily, but designless has the advantage that you can't make mistakes in the design. You can be quite defect tolerant. But on the other hand, you have to, of course, to train every and each individual device, which comes with a cost. So hopefully with that, we can arrive at a new paradigm, a new generation of computing that may hopefully contribute to this huge issue of unsustainable energy consumption that I've showed in the beginning. Thank you very much for your attention.